In this video, I want to talk about the problem of variable selection. So let's say for each object, for each record, we have a large number of variables. So say we're talking about houses. And let's say specifically we're talking about the sale price. This will be our output variable. So for house 1, the sale price is going to be Y1. For house 2, the sale price is Y2, and so on. Now, the sale price of a house depends on a great many factors that we may have recorded. For each house, we record a long list of properties. For instance, square footage, lot size, number of bathrooms, number of bedrooms, number of doorknobs, just making things up, etc. So we can put all this data into a really big chart. So house, house 1, house 2, house 3, and maybe we'll call square footage. That will be our variable x1. So if the square footage of the first house is 2,000 square feet, that's going to be x11. First house, first variable. Let's say the lot size in, let's say, acres, hectares, whatever you want to measure the lot size in, square feet. The lot size is sometimes measured in square feet. This is going to be our variable x2. And so let's say we have 0.5 acres. This will be my first data point, but second variable. And so on. Number of bathrooms, there are 2 bathrooms, this is x13. And so on, dot, 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 lots and lots of columns. And then there's a sale price. So Y1, whatever this house sold for, $150,000. And then we have all the data for house 2, all the data for house 3, all these properties, and the sale price. Now, let's say we have n input variables. So there are n columns before our y. So our input variables are x1 to xn. And let's say we have m houses. Remember in our last video, m was the number of data points. So house 1 through m. We could do a linear regression with all these variables as our input variables and y is our output variable. If we just had one input variable, just x1, we'd have like x1 on the horizontal axis and y on the vertical axis, and we'd have some data points with the square footage and their sale prices. So the square footage would tell you how far you are over, and the sale price would tell you how far you are up. We'd put a data point there, and we'd try to fit a line of best fit to it. If we had two variables, square footage and lot size, then we'd have two horizontal axes and one vertical axis, and we'd end up with a whole bunch of points in R3 in space, and you try to fit a plane of best fit to it. If you have three input variables and one input variable, now we can't visualize things very well. We can still do the math, and you could still have Excel or R figure this out for you. We have three input variables and one output variable, you'd fit, technically it's called a hyperplane, but the name doesn't really matter. And you could do all your stuff where you figure out the coefficients. What do you multiply square footage by? What do you multiply a lot by? What do you multiply this by? And what's your y-intercept? And that gives you a hyperplane, and so on. And we could use that. And then we could take a look at r squared to see how well that thing fits. And then we could do the same thing with 4 input variables or 5 input variables. And it quickly becomes impossible to visualize, but just as easy to do the algebra for. Now, if we take a look at these variables, some of them are probably going to be quite important to y. And some of them probably won't be. The number of the square footage, probably important. The number of bathrooms, probably important. The number of doorknobs, probably less important. If somebody went through the house and counted the number of light switches, probably not so important. I don't know how much a buyer wants to know about the number of light switches in the house. If somebody went through the house and counted the number of rooms painted pink, I don't know how important that is to a buyer. Maybe that's like a negative thing. If too many rooms are painted pink, I don't know how many buyers are going to be interested in buying this house. So you'd have to have a very specific buyer who has very specific tastes. So some of these variables are going to be important. Some of the variables are going to be less important. And what we want to do, so the main problem, and I see I'm kind of running out of board space, so hopefully you have this all in your notes. Is this. Find a subset of the variables that contains all the important variables. And leaves out the unimportant variables. Now, this is more complicated than it sounds because some variables might be important in groups. So let's say we're talking about a house. The number of bathtubs and the number of showers are important, but the number of bathtubs plus the number of showers is more important together, because if you don't have any bathtubs, it could still be okay if you have some showers. And if you don't have any showers, it could still be okay if you have bathtubs. So these two variables are important together. And so this is a harder problem than you might imagine. But let's say you have 100 variables. Say there are 100 variables. There are a large number of subsets of the variables. In fact, a huge number of subsets of the variables. Let me explain why. Let's say we just have two variables. Let's start with just two variables. Let's call them variable x1 and x2. Let's take a look at all possible subsets of the variables. Well, you could have none of the variables. So that's supposed to be an open set and closed set. So there's no variables in there. That's one possible subset of the variables. Take none of them. You could also have just the first one. You could also have just the second one. And you could have both. Oops, sorry, this one was supposed to be just the second one. And then you could have both. So if you have two variables, there are four possible subsets of the variables. None, just the first one, just the second one, and both. If you have three variables, so let's call them x1, x2, x3, you could have none. You could have just the first one, just the second one, just the third one. You could have the first two, the first and the third, the second and the third, or all of them. So here there were four possibilities, and here there were 8. If you have 4 variables, you'll find out that there are 16 possible subsets. If you have 5, it's 32. The number of possible subsets is always 2 to the power the number of variables. This is 2 squared. This is 2 cubed. So if you had 100 variables and you were going to look at all the possible subsets, there would be 2 to the 100. There is no computer on Earth that can count that high in a reasonable amount of time. This is a number with, what, like 30 zeros after it. I mean, it's like a 30-digit number. It's huge. And so we can't just test every possible subset. But in this video, I want you to get the idea that what we're looking for is a subset that contains all the important variables and none of the unimportant variables, and that the total number of subsets that you could possibly check if you have a large number of variables, and 100 is pretty modest. You might have many more records than that. It's just prohibitively big. Even with just 10, there are like 1,000 subsets. If you have 20, it's like 1,000,000 subsets. This gets big fast.